All right, when you left, we had just finished gathering our class data for topic 13, number 1. So this is what our class graph looks like, which is part G. Part H and I is commenting on how this is shaped. It's hard to see with this graph, mainly because our sample size is relatively small, of only around 40. But this graph is almost symmetric. It's not skewed. It doesn't have enough of a tail to one side for us to be able to call it skewed. It's almost a normal distribution, just not quite. Okay, so what we're going to look at is part 13.2. If you look in your book, this is on page 272. And here, what we're going to be looking at is an applet online, and I gave you the link to all of the applets. I printed out the pieces so that we can look at them as we work through. So we want to open the Reese's Pieces applet and select sample size 25, and we're going to assume that our population proportion pi is equal to 0.45. And then they want us to draw one sample at a time and see what we end up with, and then draw 4 more samples, recording the value of the sample proportion each time. Now, are those always going to be the same? Probably not, and that's because of the idea of sampling variability. Remember, every time you take a sample, it's going to be different. You might not necessarily have the exact same sample proportion as someone else. And we notice that with this graph here. People did not always get the same exact proportion. Some people even had 2 samples and ended up with 2 different sample proportions. So the next part, for part C, it says, okay, do it a total of 500 times. And that's what I have for you right here. So right here, this is a printout of what that applet can show you. Notice I have the probability of orange is set to 0.45. That's that pi, right? And remember, pi is your population proportion. And then here, the number of candies, that is my sample size. That's my N. And I have a total of 500 samples. So if I look at this graph, do you notice any pattern of this? When I look at it, I notice it definitely looks pretty symmetric. And the center is somewhere between 0.4 and 0.48, which pretty much makes sense given what my population proportion is. Now, the next step says to plot the normal curve. So I have that right here. So comment on how well the curve appears to model the distribution of the simulated sample proportions. If I look at this, it doesn't fit it perfectly, right? We have some that are above and some that are below. But it does fit it reasonably well. If I was to draw a curve, especially a nice, smooth, pretty curve like this one, this is going to be my best fit. So does the sample proportion for part F appear to provide unbiased estimates of the population proportion? For unbiased estimates, that showed up way back in topic 4. The idea of an unbiased estimate is if I take a bunch of sample proportions, they're going to be centered around what my population proportion is. There are some statistics, such as standard deviation and range, where if I take a lot of samples, those sample statistics, my sample standard deviation and my sample range, they don't gather around what my population would be. But a proportion is an unbiased estimator. For part G, it wants you to record the mean of our p-hat values and the standard deviation. That's these values right here. So the mean of our p-hat values is 0.452, and our standard deviation, mean, oh, I can't even read that, and then the standard deviation is 0.096. So would you say that most of these sample proportions are reasonably close to 0.45? Which is right about here on this graph. I would say, yeah, there's some of them that are farther away, right? But most of them are here in the middle. So the next part is we're going to look and see what happens when we change our sample size. The sample size for this is going to be 25. That's what we just did. And now what do you think is going to happen when we change it to 75 instead of 25? So we are going to end up with a larger sample size. And take just a moment and think to yourself, what happens when we have a larger sample size? If we have a larger sample size, we tend to have less of something else. Okay, so having that thought in your mind, let's go ahead and look and see what my graph and everything looks like when I've got a sample size of 75. So here, my probability of orange is still 0.45. The number of candies, in this case, is now 75. Remember, your sample size is n. And I drew 500 samples. And my shape looks pretty darn similar, right? And then my mean and standard deviation. Notice what has changed here. My mean this time is 0.447, and my standard deviation is 0.055. Okay? So how did that change from the previous one? I'm going to set these to the side, and I'm going to write down both of these together so that you can really see what they are. When our sample size was 25, our mean was 0.452, and our standard deviation was 0.096. When our sample size was 75, the mean was then 0.447, which those are pretty darn similar. They both round to 0.45. They're very close to being the same. But my standard deviation this time was now 0.055. My standard deviation has gone down almost by half, not quite, but almost been cut in half. So if I have a larger sample size, remember that leads to less variability. A larger sample size means less variability, which means a smaller standard deviation. So the main idea that we're looking at here is the central limit theorem. Now notice, what do these shapes all look like? Right? For the sample size 25, we've got this nice normal distribution. And then once I overlay the normal distribution for my sample size 75, notice that also fits it fairly well. So when we're looking at the central limit theorem, we have a couple of things to consider for when we can use it and how it helps us. So for the central limit theorem, for a sample proportion. And remember, sample proportions, those are called p-hats. If you forget about those, remember there's that table in the beginning of topic 13 that has all of our notations. You are going to want to become familiar with those. Now, the first step in looking at the central limit theorem is we have requirements that must be met. The first requirement is SRS. And remember, that stands for simple random sample. Now, your sample, it doesn't necessarily need to be simple random sampling. You could have random assignments. You could maybe have some stratified samples. All that matters is that you have an unbiased sampling method. You have to have a valid sample or else none of this stuff matters. The second requirement, and this one it might look confusing, but as we practice it, you'll see what it means. We've got n times pi has to be greater than or equal to 10, and n times 1 minus pi has to also be greater than or equal to 10. All that means is that we must have a large enough sample size, and as I said, as we move forward, you'll see why. Now, the second part is really what the central limit theorem will tell us. So, the central limit tells us that, or the central limit theorem tells us that if my requirements are met, that the sampling distribution, the sampling distribution of all of my sample proportions will be, right? And then we have a couple of things that it tells us. It tells us the shape of it. It tells us where the center is going to be. And it also tells us what our spread looks like. Now, this is helpful. Remember when we describe a distribution, we talk about the shape, the center, and the spread. So the central limit theorem tells us that the sampling distribution of all of my p-hats, so all of those possible sample proportions, the shape of those is going to be approximately normal. And we saw that on those graphs. Now the center is going to be equal to the population proportion. That is pi. So the mean of all of my p-hats is equal to pi. Now remember, this is not pi as in 3.14. This is your population proportion. So when we look back at those graphs, we set our population proportion to 0.45. And remember, that's where our graphs were centered around. Now this symbol right here, once again, that table in the beginning, will tell you that this is mu, which is a population mean. So that just means that the population mean of all of my p-hats, which is going to be the center of my distribution, is going to be equal to that population proportion. The next piece is the spread. And remember, spread, we are going to be using standard deviation to talk about spread. And these ones so far have been really straightforward, really quick and easy. This one we have a formula that we're going to be able to figure out. So the population standard deviation of all of my p-hats is equal to the square root of pi times 1 minus pi all over my sample size. This formula looks a lot more complicated than it actually is. As we practice this a couple times, then you'll notice it's really not nearly as bad as it seems. Okay? So for the problems that we've already done, let's go ahead and let's see if we can sketch these distributions and see what the central limit theorem will tell us for these problems. So if I'm looking at my sample size of 25, the very first simulation that we did, our sample size was 25, and our pi was set to 0.45. Right, this was our first simulation. So if I'm going to use the central limit theorem, we want to know, what does the central limit theorem, or the CLT, tell us? And remember, our first step is, can we check those conditions? Well, I want to check and see, is n times pi greater than or equal to 10, and is n times 1 minus pi greater than or equal to 10. So my sample size was 25, and pi is 0.45. Is that greater than or equal to 10? Yes, it is. This is one where we don't necessarily, unless it's really close, we don't have to really calculate it. I don't really care what that number is. I just need to know, is it going to be bigger than 10? This is almost half of 25. It ends up being around 11. It's bigger than 10. My next piece is looking at 25 times 1 minus pi. So that's 1 minus 0.45. I like to do these in my head. I like to just think about percents. So 1 minus 45% gives me 55%. Is that greater than or equal to 10? Well, of course it is, because this smaller one is bigger than or equal to 10. Okay, so now the central limit theorem will tell me the shape is going to be approximately normal. My center, I know that my mean of all of my p hats is going to be equal to pi. And what was pi in this case? Well, 0.45. And then for my spread, that's going to be calculating that standard deviation. So the sigma sub p hat, the standard deviation of all of my p hats, is equal to the square root of 0.45, right? Because I've got pi times 1 minus pi, so that's times 0.55, divided by my sample size, which is 25. And I get 0.0995. This was a 4, but it rounds up because it's 49. Now, if we look back and we compare that to what we had for our simulation, let me skip these over, get them on the same thing here. So this was my simulation. My mean was 0.452, which is really, really close to 0.45. And then my standard deviation, this was 0.099, this was 0.096. Both very, very close. Okay? Now, I can sketch this distribution as well, just so that I can see what this picture is going to look like compared to the simulation. My mean, this is going to be my 0.45. Remember, this is just your normal distribution from before. Then this is 0.5495. I'm just adding one standard deviation as I go. This is 0.649. Then this is 0.7485. Going back the other way, I subtract one standard deviation. This is 0.3505. 0.251, 0.1515. All right, so if we compare that to that graph that we looked at earlier, notice this graph goes from about 15% to about 75%. And notice this graph where it goes from about 15% to about 75%. I have the same shape, I have the same mean, and around the same standard deviation. It's not going to be perfect because this is a simulation and we have sampling variability, but it is pretty darn close, which is what we hope for. Okay? So looking back at that central limit theorem, the really important piece for these is it tells us our shape is going to be approximately normal. The center of that normal distribution is going to be centered around my population proportion. And the spread, that standard deviation, is going to be equal to this formula right here. My population proportion times 1 minus my population proportion divided by n, and then take the square root of the whole thing. This piece, taking that square root, from what I've noticed in class, that's the piece that gets forgotten when people are plugging it into their calculator. So make sure to pay attention right there. So looking back towards the book, I know I've gotten off a little bit from where they were at, but that's okay. The next piece is, what do you think is going to happen if we have a population where the population proportion is 25%? So based off of that central limit theorem, how do you think it's going to change if your sample size is still 75? Now, when we had our sample size of 75 and our population proportion was 0.45, notice our mean was 0.447, or about 0.45, and then that standard deviation was 0.055. Now, if I just change this to 0.25, how do you think this is going to change this distribution based off of that central limit theorem? So think about that for a moment. And let's see what happened. So for this, notice where my mean is now. My mean is now exactly 0.25, which that makes me pretty happy. It's always nice when a simulation works out exactly how we want it to. And then my standard deviation is still right about 0.05. It's a little bit smaller, but it still is pretty close to what it was before. So our standard deviation did not change much, but our mean changed a whole lot. It shifted the entire distribution down by where that 0.25 is. Okay? So if you look at, this is a bad picture, and this is the same one you have, it just didn't copy very well, but for page 276, this is where the book gives you the central limit theorem. One thing that the book does is they kind of downplay how important the conditions are for using this distribution. The conditions are something that are incredibly important, and we really want to stress them because as you move forward with collecting your own data, those conditions of n pi greater than or equal to 10 and n times 1 minus pi greater than or equal to 10, those are going to be incredibly important for you. So the next piece, I'm going to skip ahead a little bit because we've already done O and P, is let's skip ahead to part R. Right? So for part R, it tells us to just first use the applet, and we're not going to do that first. Instead, what we're going to do first for part R is we're actually going to use the central limit theorem and see if we can find what it would tell us if, in this case, our population proportion is 0.1, or 10%, right? And my sample size is 25. Okay? So in this case, my shape is going to be approximately normal. My center, remember my center is going to be right around, it's the mean of all of those p hats, it's going to be centered around pi, which is 0.10. And then my spread, so the standard deviation of all of those p hats, I have a formula, right? And that's the square root of pi times 1 minus pi all over the sample size. So the square root of 0.1 times 0.9 divided by 25. Which is exactly 0.06. It's a nice, pretty number. So now I'm going to use that central limit theorem to sketch that distribution. So here is my mean, which is 0.1. And then I'm going to go up by 0.06. So this is going to be 0.16, 0.22, 0.28. And then going backwards, I've got 0.04, negative 0.02, and then negative 0.08. Now, just for a moment, I'd like you to look at these numbers down here. Remember, all of these represent sample proportions. These are all p hats. And so see if you can think of what might be the problem there. What is going on that's making this not be nice? And the issue's right here. Can I have negative proportions? Remember, a proportion is a percent. Does it make sense that you could end up with a negative 2% of your sample has orange? That doesn't make sense. We can't have a negative proportion. So something weird is going on here. And when we use the applet, this is what we come up with. Now notice, these numbers are the same as what I came up with. My mean is almost, this is 0.098, which that's approximately 0.1. My standard deviation is approximately 0.06. That's almost exactly what I came up with, off by a thousandth or two. So my numbers are right, but this is not a symmetric distribution. This distribution is skewed right. Remember, that means pushed from the right. So when I'm looking at this, I have to figure out why that wouldn't be true. Why is this not a normal distribution? And it goes back to the importance of checking our conditions. I did not check conditions here. And if I check my conditions, n times pi, if I check to see is that greater than or equal to 10, I've got 25 times 0.1 greater than or equal to 10. 2.5 is not greater than or equal to 10. My conditions are not met. So if my conditions are not met, that means that my central limit theorem is not valid. I can't use it unless those conditions are met. Now, when we compare this and we say, okay, well, what if we were to raise our sample size? What if we were to change our sample size to 250? So we're going to make it 10 times as large. Would that change much of my problem up above? Well, I know that my conditions would now be met, right? Because 250 times 0.1 is just 25. So our conditions would be met, which means that we could use our central limit theorem. The mean of all of my p-hats would still be 0.1, but my standard deviation of those p-hats, that would change quite a bit. I would have 1 minus pi, pi times 1 minus pi all over n, which is, instead of n being 25, as it is up above, it's now 250. So I've got 0.1 times 0.9 divided by 250. Which is now 0.01897. I'm going to round that to 0.02 just for the sake of getting this quick. So this right here is 0.1, it's my center, and then I'm going up by 0.2, so 0.12, 0.14, 0.16. Oh, I'm sorry, you can't see that. There we are. And then 0.08, subtracting 0.2 as I go to the left, 0.06, 0.04. Notice, do I have any negative proportions now? And I don't. That's because my sample size is large enough that I end up with a small enough standard deviation that I don't end up going past that 0. And if I use the simulation, notice this one, now it's nice and normally distributed. And if I look at that normal overlay, it looks nice and pretty. Okay? So hopefully this helps you with problem 13.